To another video. My name is Codeforces, and in today's video we're going to be doing problems A, B, and C from this contest round 842, contest 1768, rated for Division 2. So let's dive straight into it. So problem A, you are given an integer k, find the largest integer x where 1 is less than or equal to x is less than k, such that x factorial plus x minus 1 factorial is a multiple of k, or determine that no such x exists. If you take a look at the sample input, you'll notice it's 3, 6, 8, and 10, and the answers are 2, 5, 7, and 9. So first, you'd be pretty safe to just guess that it's just whatever the number is minus 1. In fact, that's the correct answer. But I'm going to just quickly demonstrate why that's the correct answer. So what you want to do is you want to observe that if I take x factorial, I can say this is x times x minus 1 factorial. So that means that x factorial plus x minus 1 factorial is equal to x times x minus 1 factorial plus x minus 1 factorial, which is equal to x plus 1 times x minus 1 factorial. So this x plus 1 term is exactly what we're looking for. If I take k minus 1, if I say x is equal to k minus 1, then x plus 1 times x minus 1 factorial is equal to k times k minus 2 factorial, which is obviously divisible by k, right? So that's the explanation, that's the reasoning why we can use k minus 1. And since the maximum x we're looking for is x less than k, that means the maximum x is k minus 1. We've proven that we can do k minus 1, and so the answer is just k minus 1. So let's code this up, a.py. I'm going to use Python here because it's so easy. So we're going to say t is equal to int of input for tc in range of t. We're going to input k. K is equal to int of input, and we just print out k minus 1. That's it. Boom. So now what we can do is we can go ahead and submit this. We will use Python. PyPy 3.6.9 is what I prefer. And you submit it, and it's accepted. So now we can move on to problem B. Problem B states you're given a permutation P of length n. In one operation, you choose k distinct elements pi1, pi2, pik. You remove them, and then you add them in sorted order to the end of the permutation. You want to find the minimum number of operations needed to sort the permutation in increasing order. So now here's the deal. For this problem, assuming that you've already tried it, there's a pretty key observation you need to note here. So let's take a look. So 2, 5, 1, 3. Actually, let's do something different. 5, 1, 3, 2, 4. What's the minimum number of operations I need to do? Let's suppose each operation only takes one number. Then what do I want to do? It turns out that the minimum is to take this 3, put it on the end, then take the 4, put it on the end, and then take the 5 and put it on the end. 3 operations. I challenge you, see if you can figure out a way to sort this that uses less than 3 operations, assuming that the size k is 1. So what did I just do there? Well, let's take a look and see if we can do it, see what the minimum is in using 2 operations. So what do? What I'm going to do is I'm going to select this 3 and this 4, move them to the end. That's going to give me 5, 1, 2, 3, 4. Then I just select this, whatever, 5, and it doesn't matter, 4. And what we get is we get 1, 2, 3, 4, 5. And that's sorting it in 2 moves. So I want you to know, both times I moved the 5, the 3, and the 4, but I did not touch the 1 or the 2. I did not touch this or this. So what's the reason for that? The reason is if there's a 1 and then a 2 and then something else, right? If there's a 1, I don't need to ever operate on that 1. As long as I operate on everything else, because I have to operate on everything else, then that 1 will eventually go to the front, right? So if I take a look, if I have this 5 and then this 5 needs to move out of the way. Because remember, we can only push elements to the right. We can only push to the right, we can never push to the left. So this 5 is going to need to be operated on. So this 1 will just eventually slide over to the left. So that's what we're going to do. We're going to keep this 1. But now what? Now, I also have a 2. Now, I can operate on the 5, the 3, and the 4. The 1 and the 2 will get shifted. So then you might say, okay, well, why don't you also keep the 3? That's because, look, if I kept the 1, the 3, and the 2, their order, their respective order would be preserved. I'd have a 1, and a 3, and a 2, and then a 4, and then a 5. That's not good. I want it to be sorted. So what I'm going to do is I'm going to look. I'm going to see, okay, I've got a 1, and then I'm going to keep looking for the 2, and then look for the 3, and then look for the 4, until I reach the end. Like, keep doing this, ... right? And each time I see a number, that's one time that, or one less time that I need to perform an operation, right? Or that's one less number which needs to be operated on. So now suppose I know that I need to operate on 3 numbers. Each operation does k numbers. So I want to make sure I have enough operations to fit those 3 numbers. What can I do? I can simply say, okay, I want to take 3 over k, and I want to take the CEAL value of it. I want to take the upper bound. For those of you who don't know what this is basically just a roundup. So 1.5, if I took the CEAL of it, that would equal 2. If I took the CEAL of 2, that would equal 2, right? If I took the CEAL of 1.1, that would still equal 2. So why do I want to take the CEAL? I want to take the CEAL because even if I have a little bit extra over, even if I have some amount additionally, I need to do another operation, right? So suppose k is 2, that's a perfect example. Then I need to have one number and one number in our first operation, and this last remaining number needs another operation. I'll need 2 operations, right? So in this case, 5, 3, 4, I will need to take 3 and 4 in one operation, and then 5 in another operation. That'll take 2 operations. So if you note, 3 over 2 is 1.5. We take the CEAL value of that. What do you get? You get 2. So now in code, the way that you do the CEAL value is if you want to take n over k and you want to CEAL it, what you do is you say this is n plus k minus 1 over k, right? And this is assuming this is the floor division, right? So this is equal to this. There's a whole lot of mathematical reasons why this works. You don't need to worry about that. You just need to remember that you do n plus k minus 1. So now we can go ahead and code this problem up as well. So let's do that. This problem also only really needs Python, but for completion I'm going to use C++. So we're going to start up, load our template in here, and I'm going to read an int n, m, sin n, m, and then vector of int v array size n for int and I and v sin I. So what did I just do there? I took in my input of n and m, and then I read in my array. This is some fancy notation to read in an array quickly. Now, I have my array. I'm going to say int L, or int L, which is basically looking for, is 1, and found is equal to 0, right? Because we've not found any. So, or rather, we can say op is equal to n, because I need to operate on n. So now I can say for int I and v. Now I can check if I is equal to L, op minus minus, L plus plus. And so now the number of elements I have to operate on decreases by 1, and I'm looking for the next number. So now, what do we check? We check. We say output L, or op, plus k, or plus n, technically. Oh, it's k, it's not n. K, right, it's k. op plus k minus 1 divided by k slash 1. And that is exactly how you solve this problem. Let's plug it into a custom invocation because I just want to make sure that this code works, right? So we can scroll all the way up to g++20, copy, paste, run. Always use this this custom invocation if you can, because it's going to reflect the actual result when you submit. So if it's really laggy, obviously don't use it. Like, it's taking a long time to give you back your results, you don't need to use it. But if you can use it, go for it, because it's going to reflect exactly what you want. Oh, I got accepted and not Happy New Year. That's sad. Oh, now I got accepted. Okay, cool. So that's problem B. Let's move on to problem C. This is the problem where a lot of people got stuck. Like, a lot of people got stuck. And it's actually a pretty weird problem. You are given an array A of n integers. You want to find two permutations P and Q of length n such that max of P I Q I is equal to A for all I, right? Or you want to report that a P Q does not exist. It's a really simple problem, or a really simply stated problem, much harder than it looks. Let's take a look. We're going to start off with randomly generating two permutations, and with those two random permutations we want to check it. So why am I doing this? If you take a look at their sample test cases, they're kind of bad. Like, they don't really reflect a good sample test case, so that's why I'm doing this. So now I have to take this L3 and go back to L2 and L1. So L3 is 7546735, 75466, and the two arrays which made it up are what we have to find. So now here's the first question. What does this 7 tell you? That 7 tells you that one of these two is going to be 7. One of these two is going to be 7. So let's say, okay, let's underscores right here, right, to represent our places. So let's say that right here, this guy is going to be 7. This guy's 7. Now, take a look at this guy. That means this has to be 7, because you can't have 7 again here. One of these two's got to be 7, so this has to be 7. All right, cool. Now let's take a look. Now next number, let's take a look at this 5. This 5 means one of these two is going to be a 5, and the other one's got to be less than that or equal to that. So we could put it either place. Let's put it up top for now. Now what does that tell you about this 5 right here? What does that tell you about this 5? That means this has got to be 5. Cool. Let's move on to the 4. Again, one of these two could be 4. Why don't we put it up top? Same for the 6 and same for the 3. So now what are we missing? I'm missing a 1, I'm missing a 2. So where can I put the 1 and the 2? I could reasonably put them in any place. So why don't I put the 1 here and the 2 here? And on the bottom, what am I missing? Well, I'm missing a 1, I'm missing a 2, I'm missing a 3, I'm missing a 4, I'm missing a 6. So I'm missing a lot of things. Now I have a question for you. Can I put a 4 here? The answer is no. No, I can't. Because this max, if I max this 3 and this 4, that's going to give you 4. So that doesn't work. So this guy's got to be less. He has to be less than 3. So why don't we place our 1 here? That way we can make sure we're safe. And we'll place our 2 here, we'll place our 3 here, we'll place our 4 here, and we'll place our 6 here. And everything works out nicely. We got our 2 arrays. Let's check. Is that what we had? No, that's not what we had. Is that bad though? It's also not bad, because you can print out any 2 arrays, P and Q, that work. These 2 arrays work just fine. So we're good. Now let's think about, what did we do? Well, the strategy we used is we placed as much on top as possible until we can't place that number on top. Then you got to place it on bottom. So let's see, just to prove that that is actually what we did, we're going to do that. We'll place a 7 here, we'll place a 5 here, we'll place a 4 here, we'll place a 6 here, we'll place a set. Oh, we don't place a 7 here. Why don't we place a 7 here? Because we have a 7 here. So what we want to do is we want to place a 7 here. And then we continue, we place a 3, we place a 5. Again, no 5, because we already had a 5. So we place the 5 down bottom. And now we just fill it in. We start 1 because 5 is less. We place 2 because 7 is the greatest. 1 on the 3, 2 on the 4, 3 on the 5, 4 on the 6, and 6 on the 7. And just like that, we filled our array. So this strategy sometimes works. I mean, it could work all the time. We don't know. So at this point, your best bet would be to go for it. Would be just send it, right? But there's a proof why this works. Let's see if we can figure it out. So 7, if we can place an element, we might as well place it there, because if we could place it somewhere else, it doesn't make a difference if we place it here. It's a greedy algorithm. So we might as well place it here. And that gives us a bound on what has to happen below. And then, if we can't place an element, obviously it has to go below, right? So if we can't place an element, that means there's got to be a flip-flop. It doesn't matter where the other one goes. So it really doesn't matter where it goes as long as we can construct 2 arrays with unknown values such that each of these exists, right? So 7, I could place the 5 here, the 4 here, the 6 here, the 7 here, the 3 here, and the 5 here. You want to fill this in, go for it. 1, 2, 6. And you want to fill this in? Let's do that too. 1, 2, 3, 4. It works out. So the strategy that we're using is we're just saying, place it, if we can place it somewhere, place it there. Because it doesn't matter where we place it. And then we fill in the rest. Now let's see what happens if we try and do that for this case, 2, 1, 1. So if we had 1 and 1, right? If we had 1 and 1, and we followed this strategy, you might notice something. We place our 1 here, alright, cool. We place a 1 here, alright, cool. Now we go in and we place our 2. We place a 2 here, but that doesn't check out. Or we place a 2 here, and that doesn't check out. But luckily, the answer is no for that test case. So what does that tell us? That tells us when we're filling in the later values, right? We're filling in, we've placed these 1s, and now we're filling in our 2s, our green colors. When we're placing those values in, we gotta check and make sure that we're not exceeding the value below or above us, because then that means it doesn't work. So let's code this problem up. This is a little bit of a longer problem, and that's just a foreshadowing that it's going to take a little bit of time to code. So let's dive straight into it. So to break it down, we place, and then we've got to check what's missing, then we've got to check what we have to fill it in and place in the least spots. So it's going to be a tricky one, but it's not impossible. Let's do it. So we read in int n, sin n, vector of int b, array of size n, for int and I in v, sin I. We've got that down, and now we take it to the next. We place. So I'm going to say vector of int p, array of size n, q, array of size n. So for int I is equal to 0, I is less than n, I plus plus. Oh, we've got to make sure we track set of int p1, p2. What have we placed in these two? So what have we placed? What have we placed? Let's check. So we'll try and place it in the first. And if we can't place it in the first, we'll try and place it in the second. If we can't place it in the second, that's a problem we gotta break. So first, we're gonna check if p2.count of v of I. That means if it exists, there's a problem. We're gonna solve no, return. Now, if p1.count of v of I, q of I is gonna equal, and actually, I'm gonna make this p1 and p2 right here, and this one s1 and s2. It's gonna make it easier in the long run, trust me. So if s2.count, if s1.count, then we're going to say p2 of I is equal to v of I. And then otherwise, p1 of I is equal to v of I. And now we've got to check. We've got to see, all right, I filled in my values here. I filled in my values, right? I've filled in my values. I gotta place these guys, and then I gotta place these guys. So here's what I'm gonna do. I'm gonna iterate, and I'm gonna see. In this top one, have I placed a 1? If not, let's place it. And then have I placed a 2? No, place it. 3? Yes. 4? Yes. 5? Yes. 6? Yes. 7? Yes. And where do I place it? Well, what I'm going to do is I'm going to create a set here. And this set is going to say, I got a 7 in position 0, 1, 2, 3, 4. And I got a 5 in position 6. And I can sort this set of pairs so that 5, 6 comes first, and 7, 4 comes first. Again, greedily placing. This greedy placement will it will ensure that if we're breaking, it's because we're forced to break, right? If we're printing out no, it's because there's literally no way for us to not print out no. Greedy is very useful here. So what I will do is I will create another set of pair of int sp1, sp2. Alright, I know names are getting a bit confusing. Just bear with me. sp2 of, or dot insert, alright. Oh, and actually, s1 dot insert, or s2 dot insert v of I, right? And then s1 dot insert v of I. We gotta do that. Now, sp2 dot insert, what do we insert? We insert a pair. That pair is going to contain v of I, and that pair is going to contain I. And we're going to do the same thing here. sp1 dot insert v of I. And now we have our sp2 or sp1 or sp2, so we can say for int I is equal to 1, I is less than or equal to ni plus plus. If s1.count of I, continue. That means if we placed it in the first one, great, continue. If we have not, we're going to take the first one from sp1. So I'm going to say auto p is equal to star of sp1.begin, sp1.erase, sp1.begin. So that's good. We've got our pair. That's what that stands for. That's what this P stands for. So now we can check. We check the ith index. We want to place I in the index here. So I'm going to say int ind is equal to p dot second. If now we check if p2 of ind. Oh, and this should be sp2 by the way. This should be sp2 because we're checking from sp2. If p2 of ind is less than I. That's a problem. We want to shout no and return. Because if p2 is less than I, because that's what we're filling in the p1's index, then the maximum changes. That's not good. And so I can just make that clear here by saying p1 of ind is equal to I. And we're done. We just have to do the same thing for 2. So we're going to say this is 2, this is 1, this is 1, this is 1, this is 2, this is 1, and boom. And now we can sell yes slash n, and we have to output both arrays, so for int I in s or p1 sout I, and then sout slash n, and then same for p2. Let's check this up here. One
5s match up, 3 matches up, 4 matches up, 2 matches up, 5 matches up. We're good to go. Let's send it. And when we submit, we get accepted. Happy New Year. It said accepted. There we go. Happy New Year. So, that's problem A, B, and C from the Codeforces Round 842, rated for Division 2, aka Contest 168. I really hope you guys did enjoy, and if you did, please don't forget to leave a like and subscribe, and let me know down in the comment section below what you want me to check out next. I do read those, I promise. And with that, I'll catch you guys in another video.